Hey everyone, this is Dr. Walker. In this video, we're going to go over an example of using Gauss's law for a problem that has spherical symmetry. In this example, we have a solid sphere of radius A with a uniform volume charge density ρ and a total positive charge Q. We want to find the electric field at a point outside the sphere. So I have written Gauss's law here. And the first step is to take advantage of the symmetry. So the charge has spherical symmetry. When that's the case, we're always going to pick our Gaussian surface so that it has spherical symmetry as well. So we're going to pick a Gaussian sphere as our Gaussian surface. We know that the two conditions hold true. The first one being that the field is constant on the surface of that sphere. We know that the field due to this charge has the same value at all points on that Gaussian sphere because they're all the same distance from the charge distribution. And the other condition is that the electric field is parallel to the area vector, call it dA. And we want that to happen so that we can eliminate the dot product in the integral. So with that being said, we pick this Gaussian sphere, so we draw a sphere around our charge distribution, and then we simplify Gauss's law. We're going to have the E being constant, so it comes out of the integral being parallel. The dot product cancels out to 1. Then we have the integral of dA equals the charge enclosed over epsilon naught. And then the integral is the surface integral here of a sphere. So the surface area of a sphere is 4 pi r squared. We're using lowercase r because our Gaussian surface has a radius with a lowercase r. And then how much charge is enclosed within this Gaussian sphere? Well, we can see that all of the charge is enclosed within that Gaussian surface. So we can just put Q. And then we have epsilon naught. And now we can solve for E. We're just going to divide by 4 pi r squared. Q over 4 pi epsilon naught r squared. And we can rewrite this if we want to as Ke, Coulomb's constant, Q over r squared. And we know that the field points radially outward from the charge distribution. So this is exactly what we would expect. The field outside a spherical charge distribution is the same as the field due to a point charge. So this applies for a point that is greater than the radius. In this case, the radius was A. Now let's take a look at the electric field at a point inside the sphere. So it's going to be a little bit more difficult. This time, we still want a Gaussian sphere because of the spherical symmetry, but we want a point inside the sphere. So we need to make our Gaussian sphere to be inside the sphere, and it's going to have a radius r again. So forget this picture. This is just not the right picture here. We want a Gaussian sphere that has a smaller radius r here. We're still going to have the electric field constant over this surface. And so we can take that out. And we're still going to have the integral of the area. That surface integral is going to give us 4 pi r squared. Now, the trick is, well, how much charge is enclosed within this Gaussian sphere? It's not the total charge anymore, because some of the charge is outside the sphere. So it's a fraction of that total charge Q. To find that fraction, we have to realize that the charge within this smaller Gaussian sphere here is going to be a ratio of the volume of that smaller surface, 4/3 pi r cubed, right? The volume of this Gaussian surface divided by the volume of our charge distribution, 4/3 pi a cubed, times Q. Right, this gives us the ratio of the total charge Q that is found within this Gaussian surface. That's going to be Q in, and then we divide by epsilon naught. And now we can go ahead and solve for E again. Let's go ahead and cancel out 4/3 pi, 4/3 pi. Let's cancel out r squared to get r here. And then divide by 4 pi. What we're going to have left is E equals r divided by the 4 pi here, 4 pi, a cubed, q, epsilon naught. And typically we would write the r on the outside simply because that's our variable. Everything else here is a constant. And we can once again write it in terms of Coulomb's constant, the 4 pi epsilon naught, so ke over a cubed times q times r, and this is going to be again in the radial direction. So this is our field inside the sphere. And now let's take a look at the third part of the problem. We want to plot the electric field as a function of distance from the center of the sphere. So plot the field as a function of r. And the radius is a here. So we said that when we were inside the sphere, that we got a straight line because the field was keq, a cubed, which were all constants, and the variable was r. So we had a straight line, and then when we're outside the sphere, the field varied as 1 over r squared. It was kq over r squared. So the purpose of this exercise is to see what the fields look like inside and outside the sphere, and to see that it is a continuous function. If you plug in r is equal to a, you do get the same value for both. And finally, let's take a look at a slightly harder problem. What if the charge density is not uniform and it is given by this function here? So the charge density varies as a function of r, it's not uniform. How do we find the electric field? In this case, inside the sphere. We could have done outside the sphere as well. I just chose inside the sphere. So what's going to be the difference here? Well, we have a sphere and we want to find the field inside it. So we're going to draw a spherical Gaussian surface with a radius r again. And the only difference is that the charge is not distributed uniformly. But we'll still have E is constant at the surface of that sphere, because at the surface of that ear there's a constant r value, so there's a constant field. We're going to have E dA, and dA is once again going to be 4 pi r squared. But now the trick is to find the charge enclosed. So we can't just say it's a fraction of the two volumes because it's not uniformly distributed. So to find the charge enclosed, we need to use our friend from chapter 5 here, dq equals rho dv. We can use this, we can integrate this to find the total charge. We know that the total charge is going to be the integral of rho dv. So what is our dq here? Well, we have this Gaussian surface. We're trying to find a total charge enclosed within this Gaussian surface here. So we can divide it up into some shells, some spherical shells, right, that have a radius dr. So that's going to be our dq. This is going to be our element, our charge element here is going to be a spherical shell. And then we're going to integrate from 0 all the way up to r to get the total charge for all of these shells. So our rho is alpha r squared. And then what is dv? Well, what is the volume of this spherical shell? You have to multiply the surface area, 4 pi r squared, times the thickness, which is dr. and we're integrating from 0 to r. Now typically we don't want the same variable here and for the limit, so we put a prime on the variable that we're integrating over. All right, so we're almost done. So it was a little bit more tricky here because we had to figure out what is this charge enclosed. We can take out the constants, 4 pi alpha, and we're integrating from 0 to r, and we have r prime squared times r prime squared, so we have r to the prime to the fourth dr prime. So what we're going to get here is 4 pi alpha, and then it's going to be r prime 5 over 5, and with the limit r here, it's going to be r to the fifth over 5 minus 0. So this is going to be our charge enclosed. And now we can plug that into our Gauss's law over here. We're going to put 4 pi alpha r to the fifth over 5. And we're going to divide all of this by epsilon naught. And now we can finally solve for e. Let's try to cancel any variables. We're going to cancel out r squared here to get r cubed. We are going to cancel out the 4 pi's. And we're going to get e equals alpha r cubed over 5 epsilon naught. And then the direction is going to be in the r hat direction again. So just to summarize, if your charge is uniformly distributed, if you're outside that charge distribution, then the charge enclosed is just a total charge. If you're inside, then you have to take a ratio of the volumes of the two spheres. But if it's non-uniformly distributed, then you need to go ahead and integrate to find a total charge before you can use Gauss's law. We're going to do more examples in the following videos with cylindrical and planar symmetry.